Welcome to the deep dive. I'm so glad you're here with us today because we have a very specific, very important mission.
We really do.
You are staring down the barrel of a massive AP Environmental Science Unit 6 test, all about energy resources and consumption.
And we know the pressure is on.
Oh, absolutely. So today, we are acting as your ultimate study buddies. We are buried in a massive stack of sources here: class lecture transcripts, excerpts from chapters 12 and 13 of your textbook, and like an absolute mountain of Quizlet study guides.
Such a ridiculous amount of flashcards.
Right. We are going straight into the key concepts, the vocabulary, and the big picture ideas so you can walk into that exam feeling totally prepared.
Yeah, we're going to unpack the physics of how energy actually works, explore our massive reliance on both non-renewable and renewable sources, and examine the major environmental disasters that have basically shaped modern energy policy.
It's a lot.
It is a dense unit, but it is also the literal engine of the modern world.
Yeah.
I mean, if you want to understand geopolitics, economics, or environmental science, you have to understand where the power comes from.
Okay, let's unpack this, starting with the absolute basics of energy. Because one of the very first things your sources emphasize is the difference between a primary and a secondary energy source.
All right, because we don't just, plug an iPad directly into a lump of coal.
Yeah, exactly. We mine coal, but how does that black rock actually become the charge in a battery?
That gap between the raw material and the device is a crucial distinction for your test. We mine primary sources like coal, oil, or natural gas, but those raw materials are usually burned to generate a secondary source, which is electricity. The textbooks refer to electricity as an energy carrier.
Energy carrier, got it.
It's simply a convenient, safe way to deliver energy through the grid directly to your devices.
Which makes electricity the middleman, but playing middleman always comes with a cost, right? The sources mention we actually lose energy during that conversion.
We do.
Which ties directly into a massive concept for this exam, the second law of thermodynamics.
Yeah, the second law of thermodynamics is essentially the universe's ultimate energy tax.
Energy tax, I like that.
It dictates that every single time energy changes form, say, from the chemical energy locked in a piece of coal, to the heat energy of a fire, to the kinetic energy of moving steam, to the electrical energy in a wire, its ability to do work diminishes.
Wow, every single step.
Every step. You can never get 100% efficiency when you change energy from one form to another. We lose some of that usable energy at every single step.
And it is almost always lost as heat. The textbook uses the example of touching the hood of a car after it's been running.
Right.
Or feeling the heat radiating off a pan when you are making a quesadilla on the stove. That heat you feel escaping into the air. That is the lost energy the second law is talking about.
Which means the entire global engineering industry is constantly fighting a losing battle against physics. They're just trying to minimize that heat loss.
And that brings us to some crucial energy math concepts. You need to know that the basic unit of energy is the joule.
Exactly.
But when we look at the big picture of whether an energy source is actually worth extracting, we have a formula called EREI.
Energy return on energy investment.
Wait, so if EROEI is the return on investment for digging up fuel, how does that math actually play out? Like if an EREI is calculated at 1.0, does that mean we are literally spending a barrel of oil just to run the machines required to dig up 1 barrel of oil?
That is precisely what it means.
Wow.
You calculate EREI by taking the usable acquired energy and dividing it by the energy expended to acquire.
So higher is better.
Much better. In the early 20th century, the EREI for coal and oil was massive. We barely had to scratch the earth to get incredible amounts of energy.
But now,
Today, as we have to drill deeper and use more complex machinery, the EROEI for fossil fuels is steadily dropping. It's really a measure of how economically viable an energy source is.
the other big concept here is energy intensity. This is a measure of our energy use per dollar of gross domestic product, or GDP.
Right, basically how much energy our economy needs to generate wealth.
And there was a really surprising modern fact in the sources about this. Artificial intelligence and Bitcoin are actively making our energy intensity worse.
Oh, absolutely. The sheer computing power required to mine cryptocurrency or train complex AI models consumes massive amounts of electricity.
Like whole power plants just for servers.
Entire server farms pulling power from the grid 24/7. It is a perfect modern example of how technological shifts change our energy consumption patterns. It forces us to generate more and more power just to sustain our digital economy.
Okay, quick summary pause. Let's lock this in before we move on. You need to memorize the definition of a joule, EROEI, energy intensity, and remember that the second law of thermodynamics is the universe's heat tax.
Perfect.
So if EROEI tells us how much energy we get back, and the second law tells us we're paying a heat tax, it makes sense why finding incredibly energy-dense fuels became so vital.
It does. Which leads us straight into the big three, fossil fuels.
Coal, oil, and natural gas.
Right. These are non-renewable resources. They exist in limited, finite quantities within the Earth's crust and take millions of years to replace.
Once we extract and burn them, they are gone.
Gone for good on any human timescale.
Yeah.
Yet they provide the vast majority of the world's energy right now because they are incredibly energy dense, easy to commercialize, and relatively simple to transport.
Let's start with coal. The lecture transcripts detail exactly how coal is formed, and this looks like prime multiple-choice question material.
Definitely.
The sources say coal forms from terrestrial plants, ancient trees and ferns, that lived roughly 280 to 360 million years ago. But it doesn't just turn into coal overnight.
No, there's a very specific life cycle under heat and pressure. It starts as peat, which is basically raw, partially decomposed plant matter found in swamps.
Okay, peat is step one.
Over time, as sediment piles on top and pressure increases, that peat compresses into a soft brown rock called lignite.
Lignite.
With even more time and pressure, it hardens into subbituminous coal, then bituminous coal, and finally, anthracite.
Anthracite?
Yeah, anthracite is the oldest, most compressed, and most energy-rich form of coal you can find.
So the timeline from youngest to oldest is peat, lignite, subbituminous, bituminous, and anthracite.
You've got it.
The pros of coal are obvious. It is incredibly easy to just shovel into a train car, transport across the country, and burn. But the cons are severe.
Very severe. The textbook highlights that coal is by far the dirtiest fossil fuel.
Burning it releases high amounts of carbon dioxide, sulfur, and trace heavy metals like mercury directly into the atmosphere.
Which brings us to petroleum, or oil. While coal comes from ancient land plants, oil formed from oceanic phytoplankton.
Microscopic marine life.
Exactly. That lived roughly 50 to 150 million years ago. When these organisms died, they sank to the ocean floor, were covered in sediment, and cooked under pressure into liquid crude oil.
And we typically extract it by drilling down into the earth.
We do. But as the easy-to-reach reservoirs dry up, the industry has moved to much more destructive extraction methods.
Like fracking or going after the tar sands in Alberta, Canada.
Yeah, the Alberta tar sands are a huge one.
The sources describe extracting a thick, molasses-like substance called bitumen from these sands, and it requires a staggering amount of energy and water to process into usable crude oil.
And we cannot talk about oil without talking about the environmental disasters.
No, we can't. Your APES test will definitely expect you to know specific historical examples here. The sources highlight 3 massive spills that completely altered environmental policy.
The first is the 1969 Santa Barbara blowout off the coast of California, which coated miles of pristine coastline in thick crude.
Just devastating.
Then there's the 1989 Exxon Valdez spill. An oil supertanker struck a reef in Prince William Sound, Alaska, dumping 10.8 million gallons of crude oil into a highly sensitive marine ecosystem.
And the ecological devastation to seabirds, otters, and fish populations took decades to recover from. In some ways, it still hasn't.
It really hasn't.
The third major one is much more recent. The 2010 BP Deepwater Horizon blowout in the Gulf of Mexico.
Right. An explosion on the drilling rig killed 11 workers and unleashed a geyser of oil from the seafloor that flowed unchecked for nearly 3 months.
Unprecedented damage to marine and coastal habitats. These events are incredibly tragic, but they are crucial for understanding the true environmental cost of our reliance on drilling for petroleum.
Which brings us to the third major fossil fuel, natural gas.
Natural gas is mostly methane, right?
Yes, mostly methane, and it is frequently found sitting in the geological layers right alongside or above petroleum. It is often branded as the cleanest fossil fuel because burning it for electricity releases only about half the carbon dioxide compared to burning coal.
Cleanest. But it is still a fossil fuel. How clean can it actually be if it is still pumping new carbon into the atmosphere? Not to mention how we actually get it out of the ground.
That is the exact dilemma. Cleanest is a highly relative term. Extracting natural gas heavily relies on hydraulic fracturing, or fracking. This process involves pumping a high-pressure mixture of water, sand, and various chemicals deep underground to physically crack the shale rock and release the trapped gas.
And the sources point out that while it provides abundant fuel, a major potential risk is severe groundwater contamination.
If the well casings fail, those chemicals, and the methane itself, can leak into the drinking water aquifers above.
Here's where it gets really interesting. With all these fossil fuels, we know they are a finite resource. They are going to run out eventually. And there is a specific graph your test will ask you about called the Hubbert curve.
The Hubbert curve is a mathematical model that looks like a giant bell shape. It predicts when global oil production will reach its absolute maximum rate.
A point known as peak oil.
Exactly. And predicts when the supply will eventually decline and run out. It visually illustrates the ticking clock on our finite resources.
Okay, second summary pause. Make sure you lock in the coal formation steps, peat to anthracite, and memorize those specific oil spill disasters. Santa Barbara, Exxon Valdez, BP Deepwater Horizon.
And visualize that Hubbert curve bell shape.
Right, so knowing our extraction methods are getting more extreme, finding alternatives isn't just an environmental goal, it's an economic necessity. Which brings us to the promise and the danger of nuclear energy.
Nuclear energy is deeply complex because it offers incredible, massive baseline power, but comes with severe risks. The energy comes from radioactive materials.
And your test requires you to distinguish between two distinct nuclear processes, fission and fusion.
Right. Fission is what we currently use in every nuclear power plant on Earth. It involves splitting a large, heavy atomic nucleus like uranium-235 into smaller fragments.
And when that atom splits, it releases a massive amount of heat.
Massive. Fusion, on the other hand, involves combining smaller nuclei together. Fusion is what powers the sun.
It promises virtually limitless power without the dangerous radioactive waste.
But humans haven't figured out how to sustain a controlled fusion reaction to generate electricity yet.
So, relying entirely on fission for now, let's look at how a commercial nuclear reactor actually works. Despite the incredibly advanced physics of splitting the atom, the plant itself is really just a very complicated way to boil water.
That's entirely accurate. Small uranium pellets are placed inside long metal tubes called fuel rods. The fission reaction inside these rods generates intense, sustained heat.
Okay, so we have these uranium pellets in fuel rods generating massive amounts of heat. But how does that heat actually charge my iPad? What is the mechanical step in between?
The heat from the fuel rods boils surrounding water to create high-pressure steam.
Okay.
The physical pressure from that expanding steam is routed through pipes to physically spin a massive turbine. That spinning turbine turns a generator, and the generator utilizes electromagnetic fields to create the electricity that flows out to the grid.
So it goes, fuel rods create heat, heat makes steam, steam spins the turbine, turbine turns the generator.
Exactly. And one of the biggest advantages of nuclear power is a term called the capacity factor.
Capacity factor is simply the fraction of time a power plant is actually operating and generating electricity.
And nuclear is the undisputed champion here. A nuclear plant runs almost constantly, day and night, rain or shine.
Compare that to a wind turbine that has to wait for a breezy day or a solar panel that only works when the sun is up.
But the catch with nuclear is substantial. First, there is the waste. Those used fuel rods don't just magically become inert when they can no longer generate efficient heat. They remain highly radioactive and incredibly dangerous for tens of thousands of years.
Tens of thousands.
Currently, low-level radioactive waste like contaminated clothing or tools is stored in facilities in places like Nevada. But high-level waste, the spent fuel rods, is a massive geopolitical headache.
The Yucca Mountain site in Nevada has long been proposed as a deep geological repository for long-term storage, but it remains highly controversial due to the sheer timeline of the danger.
And then there are the catastrophic meltdowns. Just like the oil spills, you need to know the three major nuclear disasters.
First is 3 Mile Island in 1979 in Pennsylvania. A cooling malfunction caused part of the core to melt, leading to a partial meltdown and massive public panic, though radiation release was relatively minimal.
Then came the big one. Chernobyl in 1986 in Ukraine.
Yeah.
A flawed reactor design combined with human error during a safety test caused a massive explosion and fire. It destroyed the reactor core and released a massive radioactive cloud that spread across Europe.
The area around the plant remains an uninhabitable exclusion zone today.
And finally, Fukushima in 2011 in Japan. This wasn't human error, but a natural disaster. A massive magnitude 9.0 earthquake and a subsequent tsunami flooded the plant.
It knocked out the emergency generators required to cool the reactors, and the equipment failure triggered 3 core meltdowns.
If we connect this to the bigger picture, nuclear energy offers incredible capacity factor and produces 0 greenhouse gas emissions during operation. But the sheer devastation of accidents, and the dilemma of safely storing toxic waste for millennia make it a deeply fraught alternative to fossil fuels.
Okay, third summary pause. Lock-in fission versus fusion, the role of fuel rods, capacity factor, and the locations of the three nuclear disasters. 3 Mile Island, Chernobyl, Fukushima.
Got it.
Which naturally leads us to look for power sources that don't involve ancient carbon or splitting unstable atoms. Let's pivot to renewable energy.
When we talk about renewables on the AP test, we have to split them into two very distinct categories: potentially renewable and non-depletable.
Potentially renewable resources like wood and biomass can be replenished, but only if we don't consume them faster than they can grow back.
Right. If we clear-cut a forest for firewood and don't replant it, it is not renewable in practice.
Non-depletable resources like solar, wind, geothermal, tidal, and hydroelectric literally cannot be used up in a human timescale, no matter how much we harness them.
Let's start with biomass and biofuels. Your textbook makes a really important distinction here between modern carbon and fossil carbon.
Modern carbon is carbon that was recently floating around in the atmosphere before being captured by a plant during photosynthesis, like a cornstalk or a fast-growing tree.
And when you burn that biomass, you are just returning that exact same carbon back to the atmosphere.
Precisely. The cycle balances out. Fossil carbon, on the other hand, is carbon that has been locked underground in coal or oil for millions of years.
Burning fossil fuels introduces entirely new, additional carbon into the modern atmospheric cycle, accelerating climate change. That is why biofuels are considered carbon neutral, assuming the farming methods themselves are sustainable.
And speaking of farming methods, the sources highlight a fascinating detail. Algae is actually the most energy-efficient crop to grow for producing biodiesel.
It requires far less land and water than corn or soy.
I love the idea of powering cars with pond scum. Let's move on to solar power. There are 3 types of solar energy you need to differentiate. First is passive solar design.
This doesn't use any mechanical devices, pumps, or technology. It is purely smart architectural design. Think of building a house with large south-facing windows to catch the low winter sun,
Adding roof overhangs to block the high summer sun.
and using dark building materials to naturally absorb and hold heat.
In contrast, active solar uses mechanical pumps to move a fluid, typically for solar water heating systems on a roof.
And then there are photovoltaic cells, or PV cells. These are your classic solar panels that capture sunlight and use semiconductors to convert it directly into electricity.
They are incredible technology, but the sources do point out a significant drawback. PV cells are expensive to manufacture, and mining the necessary silicon and heavy metals involves toxic chemicals and significant environmental disruption.
Next up is hydroelectric power. This is using the kinetic energy of moving water like a dammed river to spin a turbine.
It is the exact same mechanical concept as the steam in a nuclear plant, but using the natural flow of a river instead.
The Hoover Dam in the United States is a classic example, and the sources specifically mention China's Three Gorges Dam as the largest hydroelectric facility in the world, generating massive power but severely altering the local river ecosystem.
And we should mention tidal energy here too, right?
Yes, tidal energy works on a similar principle to hydroelectric, but it harnesses the kinetic energy of ocean tides coming in and out.
Then we have wind and geothermal. For wind energy, your notes mention that Denmark leads the world in the percentage of its electricity generated by wind turbines.
Geothermal is fascinating because it doesn't rely on the sun or weather at all. It uses the natural, slow decay of radioactive elements deep in the Earth's core.
That decay generates immense heat, which warms groundwater. We can tap into that superheated water to heat homes directly or use the steam to, you guessed it, spin a turbine.
Always spinning a turbine. And finally, hydrogen fuel cells. Think of a fuel cell like a battery, but instead of dying, it runs forever as long as you keep adding fuel. In this case, hydrogen gas.
The only byproduct that comes out of the exhaust pipe is pure water. It sounds like magic. But what is the catch with the energy math there?
The catch is the EROEI. Free hydrogen gas doesn't just exist in abundance in nature, it is locked up in water or natural gas molecules. Right now, it takes a massive amount of energy to split those molecules and produce the pure hydrogen gas in the first place.
Often requiring more energy than the fuel cell ultimately gives back.
Exactly.
Okay, fourth summary pause. Review passive versus active solar, modern versus fossil carbon, and non-depletable versus potentially renewable. We are in the final stretch. Let's talk about energy conservation and the future.
The sources make a really helpful practical distinction between energy efficiency and energy conservation.
When your parents yell at you for touching the thermostat to make the house warmer in the winter, that is energy conservation. You are actively altering your behavior to just use less energy.
Efficiency, on the other hand, is getting the exact same amount of work done with less power, like swapping out old incandescent light bulbs for LEDs.
On an industrial scale, one of the most important vocabulary words for improving efficiency is cogeneration.
Remember how the second law of thermodynamics means power plants lose a massive amount of energy as heat?
The heat tax.
Right. Cogeneration is when a facility captures that leftover heat, the steam that has already passed through the turbine, and uses it to physically heat nearby buildings, rather than just letting it vent uselessly into the atmosphere.
It drastically improves the overall efficiency of the fuel being burned. Now let's talk about the grid itself. The electrical grid has no massive battery attached to it. It has to perfectly balance supply and demand in real time.
And a utility company's absolute worst nightmare is something called peak demand.
Peak demand is the greatest amount of energy needed by the public at any one single time. Like a 90-degree summer afternoon when every single air conditioner in the city kicks on simultaneously.
If the power plants cannot generate enough electricity to meet that sudden spike, the grid fails, and you get rolling blackouts.
To fight this, engineers are trying to transition us to smart grids. A smart grid is a computer-managed network that knows the real-time status of energy supply and demand.
It can distribute energy more dynamically and even communicate with smart appliances in your house to run the dishwasher or washing machine in the middle of the night when overall grid demand is low.
But technology alone isn't enough. Human behavior has to change. The textbook impartially outlines how governments use policy tools to force that change.
They generally use a mix of penalties and rewards. Governments can implement taxes to artificially raise the price of fossil fuels, discouraging their use.
Conversely, they offer tax credits, essentially giving citizens money back on their taxes to encourage them to buy electric vehicles or install PV solar panels.
And utility companies use a billing system called a tiered rate system. In a tiered system, you pay a very low rate for your baseline essential electricity use. But the more electricity you pull from the grid, the higher the rate you are charged for those extra kilowatts.
It is designed to hit heavy energy users right in the wallet to financially force conservation.
What's fascinating here is how all these pieces, the physics, the geology, the engineering, and the economics, have to fit together just to keep the lights on.
So, rapid fire review time. If we pull all these threads together for your test, EROEI dictates if a fuel is worth digging up.
The second law of thermodynamics guarantees we will lose energy as heat along the way.
The Hubbard curve tells us our cheap oil is running out.
Fission provides massive capacity, but leaves us with toxic waste.
And the massive disasters from the Exxon Valdez to Fukushima remind us that the stakes are incredibly high. Cogeneration captures waste heat to increase efficiency.
And while non-depletable renewables like solar, wind, and tidal offer a way off the carbon cycle, integrating them requires navigating peak demand, utilizing smart grids, and fundamentally redesigning our infrastructure.
So what does this all mean? It means you are now armed with the vocabulary, the underlying logic, and the historical context to completely master your Unit 6 exam. You understand not just what the terms mean, but why they matter.
And we want to leave you with one final, lingering thought to explore on your own. If the Hubbard curve guarantees that easy petroleum will eventually peak and run dry, and if commercial nuclear fusion remains an impossible dream for the near future, how will your generation ultimately redesign the global energy grid before the fossil fuel clock runs out? What will that physical transition actually look like in your daily life?
Something to mull over. Good luck on your AP Environmental Science exam, and thanks for taking this deep dive with us.